This lesson continues our discussion on simple harmonic motion. In particular, we're going to focus a little bit more on calculating the period for the mass spring and the pendulum, as well as applying the simple harmonic motion principles to other systems. Okay, so just to remind ourselves, okay, the period of a pendulum is only approximately simple harmonic. Okay, so the restoring force is roughly equal to the displacement only when the angle of displacement is relatively small. Less than 10 degrees is the rule of thumb that I use. When you start to get greater than 10 degrees, then the period, our calculation for the period starts to get less and less accurate. At some point, we wouldn't even call it simple harmonic motion anymore. Okay, and the only two things that the period is going to be dependent on are the length of the pendulum and the acceleration due to gravity. So just a question to get some practice. Does the period of a pendulum increase, decrease, or stay the same when the following variables are increased? Okay, amplitude, mass of bob, length of the string, gravitational acceleration. Okay, increase, decrease, or stay the same. And we'll talk about that in class next time. Hooke's law, on the other hand, okay, Hooke's law describes the force of an ideal spring, okay, and we're given by this formula that says force is equal to minus k delta x. Okay, where x is in the direction of displacement, the force is trying to bring it back to equilibrium. That's all the minus sign means. Okay, k is the spring constant in newtons per meter. Most of our springs are fairly weak, at somewhere in the order of 1 to a couple hundred maybe newtons per meter. Stronger springs definitely exist. Okay, so just to get some practice, I have a mass that's hung from a spring and it stretches. And what I want you to do at home is to calculate the spring constant for this spring. Okay. So because simple harmonic motion is given as a force is proportional to minus delta x, this mass spring matches that definition perfectly. Okay, so my force is going to be equal to some constant. In this case, the constant is the spring constant. Some constant times delta x with a minus sign involved. Okay, so that brings us to the period of a spring. Okay, the period of the spring is 2 times pi times the square root of the mass hanging on and divided by the spring constant. It really doesn't matter whether I'm vertical or horizontal, okay, and the mass is going to be in kilograms. The spring constant is newtons per meter. Okay, so here's a question for practice. I have a spring constant and I have a mass. Calculate the period of this oscillation. Okay? So the rest of these slides starts to get into how do I apply this to other simple harmonic systems. Okay, so for all simple harmonic motion systems, okay, that formula of force being proportional to minus delta x, or my acceleration is basically going to be equal to minus some constant times delta x. Okay, since force is mass times acceleration, it's c generally has a mass involved, but not always. Okay, so the coefficient c, okay, that's all it is it's a coefficient. The coefficient c is going to be equal to the square of the angular velocity. Okay, so c is equal to this Greek letter omega. Okay, it kind of looks like a curly W. Okay, that constant c is equal to omega squared, and my acceleration then is nothing more than minus omega squared delta x. Okay, that angular velocity you've seen in math if you've gone through the sines and cosine waves. Okay, in math we treat it a little bit differently. Okay, we generally don't use the Greek letter omega. We use the, I want to say our math class uses the letter B to represent angular velocity. Okay, but angular velocity is the number of radians traversed in 1 second. Okay, remember there are 2 pi radians in one circle. So omega is going to be 2 pi radians per circle times the frequency of revolution. Okay, so the frequency is in circles or revolutions per second, and since f, the frequency is equal to 1 over period, omega is nothing more than 2 pi divided by the period t. Okay. When we look at it from a math standpoint, okay, the position can be viewed as a sine or a cosine function. And we generally treat our position function x, okay, as being some amplitude a times cosine omega t, okay, where omega represents the frequency. Okay, actually 2 pi times the frequency. I believe, like again, math class uses the letter b. Okay, but this is how we derive the mass spring period from this function. Okay, if using Hooke's law, if F is equal to minus k delta x, and that's the only force, then I have mass times acceleration equal to that. Solving for acceleration, I end up with acceleration is equal to minus k over m delta x. Okay, but remember, acceleration is nothing more than, that constant k over m is my omega squared. Okay, so making the substitution of 2 pi over t for omega squared, and then rearranging, I basically end up with t squared is going to equal the quantity 2 pi squared times m over k. Okay, it's not k over m because I multiply both sides by m, divide by k. And then taking a square root of both sides, I end up with my formula that says the period of a mass spring system is going to be equal to 2 pi times the square root of the mass divided by the spring constant k. Okay. And so I can extend this to other systems. Okay, the same approach that I took can be applied to other systems as long as I have a function that says force is equal to some minus constant coefficient c times delta x. I can do the same approach. Okay, calculate my acceleration. Acceleration is equal to minus c over m, whatever that constant c happens to be, times delta x. Omega squared, again, gets equal to, set to that constant in front of the delta x, and that's 2 pi over t quantity squared. And then solving for t, I'll find some sort of equation that says the period of this simple harmonic motion system is 2 pi times the square root of the mass of the object divided by that constant c. Okay, in the case of a pendulum, the mass actually cancels out on both sides because there's a mass in that constant c, and that's why that kind of disappears in the pendulum system. Okay, and this is how I can apply that formula to other systems that are simple harmonic motion. Okay, thank you.